question. All right, so in this example, if I'm sitting here, it's my turn, I get to choose. Do I want to go to a state in which I win, assuming that I make no mistakes? Do I want to go to a state in which I lose, no matter what I do? Or do I go to a state where it's a stalemate, where we play forever unless somebody makes a mistake? Which way do I want to go?
That way.
I want to go this way. So this is what I mean by you don't do a stupid thing, is you always go that way if you can. Now, so in this case, do I win or do I lose? I win, right? I win because there's an edge to win. Right? And in this case here, do I win or I lose?
Lose.
I lose, right? So here we label this 0 win, we label this 1 win, and now in this case, which direction do I want to go? Do I want to go a direction where I lose or to a direction where we have a stalemate? Right? I go to a stalemate, and what's going to happen? Well, we're going to have a stalemate, right? So that's what I was hoping for the first question. And then what's the algorithm? The algorithm is, well, the nodes that you're guaranteed to lose, if 0 win, the game's over and 0 wins, then it's a 0 win node, right? You label those bottom ones in the obvious way. And then you apply these rules in the obvious way. And then when do you get stuck? You get stuck when, if you, right? Are you ever going to be you're never going to be able to apply this rule. Why? It's because when do you get your first stalemate? You only get a stalemate if you have a stalemate. Right? So you're never going to be able to apply this rule. So you keep applying these two rules until you can't apply rules anymore. And then any node that's not labeled, you label stalemate, and then you do a little math and you prove that it works. And that last math I didn't expect anybody to get. Alright, so I was frustrated with. Most people that I read didn't get this, so they were confused about something bigger. And so that's about that problem. But about the algorithms in general, what I got frustrated with is that most of them that I read basically gave me the algorithm, the code for depth first search or breadth first search. And then they kind of added some steps for good luck. Right? Now what does that mean to me? That means to me that they're not thinking about this problem the way I want people to think about it. Alright? The way I want people to think about it is, what's my loop invariant and how do I simply make progress while maintaining the loop invariant? Right? And so that's a different way of thinking about it than, it's hard for me to read people's minds, but my assumption is that the person who writes down the depth first search algorithm is thinking, oh, I need an algorithm. I don't know many algorithms. What can I possibly do? Well, he taught us depth first search. So maybe depth first search is the right algorithm. Let me write down the code for depth first search. Right? Let's think about algorithms. Right? Think about code as opposed to think about loop invariants and how to maintain them. So anyway, what's the bottom line is, whatever. Hopefully I will learn, we both need to learn something. Alright? What I need to learn is how to give a test where everybody won't fail. Right? And I've been trying to learn this for 15 years and I still haven't learned it. But someday I may learn it. Maybe hopefully by the exam. Alright? And for those of you who don't, everybody should work a little bit harder learning how to think about algorithms as loop invariants. And think about the examples. I'll tell you one of my problems in life, right, is I have this feeling that I shouldn't put on questions on tests that I've used in the last few years because you all have copies of them. And that means I have to come up with a new problem every time. And the problem with that is it's hard because I get bored. I think, oh, that's too easy, right? Or that's, so to come up with something that seems interesting, then it's usually too hard. Right? So that's one reason I'm asking people for these tests solutions. Don't give them to your friends, because then some days I can figure out which questions are easy and use them every few years. I mean, just as a survey, how many people have tests that I've written in the last few years? Anybody? Oh, good. Well, then that's actually, if I can trust you, then that's good for you, right? Because tests that I've used a few times, I have a better sense of, oh, well, they didn't all bomb at that time. Maybe we can reuse it. Any questions about these tests? This test?
Well, I went into it thinking that we need to memorize the algorithms that we discussed in class.
Right.
And then somehow we need to incorporate that into our answers.
Right.
So I was thinking it was going to be some kind of question that you would ask us, like, is this depth for search or breadth for search? And then we use one that I didn't think of, like I didn't study in the terms of you have to create a whole new algorithm yourself and then use a loop invariant steps.
You do.
Yeah.
You're always going to have to come up with totally new algorithms.
Yeah.
Right? So that's the whole thing here is the algorithms that you've learned in some ways are useless because I'm not going to give you one of those.
Right, exactly.
Right? In fact, just the opposite.
Yeah, that useless point is right up my alley. Exactly saying. So,
Right.
How do we make progress on the fact that that's useless? Try and have something that's useful. Like, how do we prep ourselves so we have useful material prior to sitting in there like 2:30, 3:30?
Yeah. Yeah. All right, I tell you my fantasy, and I could be wrong with that. Right? My fantasy is that if you trust the steps, it's sort of a religion here on my part, right? I'm a very religious guy here, You got to believe, right? So my fantasy is that this wasn't hard, right? So some reason people weren't getting this right.
Yeah.
Right? And I read a couple dozen of them, and most people didn't say this. So the fantasy is that had you gotten this, maybe I should have given a bigger hint that this is what you should have done. Maybe I should have drawn these pictures.
Yes,
but
I think maybe if you draw the picture, maybe
people would have gotten it.
Yes.
Right? Exactly. And so that's one of the things that I do. In fact, when I go home today, I will draw the pictures and I'll put them in this file so that if I ever use it again, the picture's there. Right? Because then I think, well, then if you trust the rules, you'll just keep doing this.
For the answer that you've got written there, you've got it set up in such a way that each player plays perfectly. So if you're in a winning position, you always win.
Yes.
And the guy that was sitting like there in the early part asked, can you assume if they played perfectly? And you said no. So you could have player 0 in a winning position and make a mistake, which would come back down.
I said no. I know at least some people asked me, and I said yes.
No, because in the early group, the guy sitting like there, you said no, and we all were like, oh, that means if player 0's in a winning position and he makes a mistake, then you either go into either a stalemate or potentially a losing position now. And so that doesn't apply based on what you had told.
I didn't say no, you said you don't need to assume because nobody's actually playing the game.
Yeah, yeah. I remember the question. Yeah, I guess what I was trying to say was that you're not playing the game, so you don't know what people are doing. But the definition of this is that 0 wins if 0 never makes a mistake. So it's assuming 0 always follows the right path.
But you had said that you can't assume that 0 will always be perfect, or that 1 will always be perfect. Because if he does, then it makes it really.
Still, it says if he does, then he will win. If he doesn't, then he might lose.
Yeah.
I think the question was too complicated.
Yeah.
Like the Towers of Hanoi one, like I understood, but like it was like a very simple question, and it still it was so complicated to like work out the details. So I think like a question as complicated. I mean, it was a simple answer, but the question had too many things that you had to consider.
Right.
And I think like I didn't even know what you wanted when I was reading it.
Right.
And like I knew you were like you didn't want anything that was like what we learned in class. Like I got that impression, but that's what I fell back on because I needed to write something.
Right. Right.
Yeah, and so I mean like the reason why I think a lot of people just
你该问的时候，
first
你走到路的时候，就是 mistake。对，这就是 mistake。没错，这就是。我一开始也不理解，最后才问他。
For sure.
他说了。
Those pictures.
这我一开始都不知道。
For example, the last step.
你知道那个老外
If
最后
the
我
state is
出去
stalemate,
的时候，
if
那老
I
外问
have
了一个
all
问题，
edges
他用了一
leading
个词，这我
stalemate,
才明白，
Uh-huh.
他用了一个
Yeah.
renaming
so it could be different. There's no one
rename the
Yeah, so I guess
status.
the point is, if I can go
他的什么意思？
to and win, then I win. If all edges lead to I lose, then I lose. And what's the case that remains is that there are no edges to win, and they're not all to lose. So there's at least one stalemate. Or all stalemates. Yeah.
How can you approach it from that mindset of, I want to go this way to win or lose? Because you said that people playing the game might not even be born yet. And so you have a neutral viewpoint of you're not trying to make 0 win and you're not trying to make 1 win.
Right.
You're just analyzing if player 0's in this position and he makes a correct or incorrect move, how is that going to affect the graph? So you can't actually really sort of say like, if I'm 0 and I'm winning, I come down here, because you're not playing the game. You're just saying if 0's here and he's winning and he makes a correct move, he'd still win.
Right.
But if he makes an incorrect move, because we're not playing the game,
He can do anything.
then he goes down here, but that's sort of not what you're saying here. Because you're saying you always want to take a winning path.
Right. So if
But
he
you're not.
always does the right thing, then he will win. He has a way of winning.
But he might not do the right thing.
Then he'll lose.
But the label means that he will do it.
How do we know if they're making a mistake?
Yes.
It says,
All I said was if he's making a mistake and if he's making a mistake, it's his turn. He made a mistake, and he's not going to win. Like player 1 has the advantage now. Because he's made a mistake. So if you don't make a mistake, you'll win. But if you make a mistake, the other person has a chance of winning.
Yeah, that's what I was
But then I was thinking like, how do I define what a mistake is? How do I figure that out?
Yeah.
What's the running time for making a mistake? Assuming player doesn't make a mistake. But then how would you ever switch? Like how would you ever switch from 0 to 1? And how would the bench switch over?
the other thing about depth first search is actually, well, I did read one person who had pretty well right, and he flipped the edges the other direction. So some sort of like, you have to work from the bottom up, right? Because the winning states you know, and then this is a state if there's an edge to a winning state, and this is an edge of, right? So it's actually, use some sort of breadth first search backwards as opposed to forwards. A lot of people started at start state S. Well, I don't know what S is, but I assume S is the start state of the game. But we don't know if that's a win until, you know. Anyway, I'll mark them. And we'll move on. Life will be good. You know, and I'll just, you know what, I'll try to make the exam questions, you know, so that they're answerable. Yeah. Right. So, and you know, actually, you want me to tell you something else that happens? I've done this many times. Right. I put on a problem that's really easy. Right. I try to think of what is the easiest question I can ever think of. Right. And then everybody gets it wrong. Right? No, seriously. You laugh, but it is a problem. And let me tell you why it's a problem. Is why they get it wrong is because they think, surely he doesn't mean this. Right? Surely something else. And they do something weird, right? That's one way to get it wrong. Right? There's another way of getting it wrong, is they think, oh, I know how to solve this. Right? So they tell me how to solve it, or they give me code to solve it. And then I say, well, that's wrong because you haven't given me the steps. You haven't proved to me that you know the steps. Right? And what I want is to convince me that you know the steps. Right? So the problem is, if it's too easy, you don't give me the steps because you can do it without the steps. And if it's too hard, you don't give me the steps because, well, you don't really understand the problem. And I just have this problem, right? You know what I'm saying? So we could make a deal here that if you promise to follow the steps, even if the problem's too easy, you know, then you know, I can try to make it easier.
I think the first thing, let us can understand your question. Yeah, for me it's difficult.
Yeah, a lot of people had a hard time understanding the question. But mind you, I did sort of stand up here in front and sort of try to explain it. You know, and people could have asked more questions.
Is algorithm
Yeah, so this guy back here obviously took it somewhere else.
No, I just programmed it before. But the problem was, I mean, that algorithm was implemented in 2 hours that we had, right? So that would have been difficult.
Sorry.
I mean, the algorithm took like a month to do, because I was, before I read up on that kind of
Right.
thing, and it took a while to invent the algorithm. So
Right.
maybe the difficulty was because we only had 2 hours.
Yeah.
Instead of a month.
Instead of a month. For sure. For sure. All right. Well, I apologize if it was too hard. We're going to do greedy algorithms. All right, greedy algorithms. Now again, let's just be clear. The greedy algorithm. You're going to have a greedy algorithm on the test and on the exam, and it will not be like any you've seen before. But I'm going to now tell you the exact paragraphs that I want on the answer. All right? And I'll tell you that some of the paragraphs will be verbatim of what we want, and some you'll have to change slightly. All right? So here, imagine we're in the test situation, and I give you the following question. I say, well, for a greedy algorithm, the input is going to be a set of objects, and in this case, the input will be a set of events. And what is an event? Event is simply, it tells you the time it starts and the time it finishes. Right? We have one room, we need to schedule these events. So, really, when you're reading the question, the first thing you should go through is say, okay, what is an object in the input? Right? And then, a solution. What is a solution? A solution is you make a decision about each object. All right, so you have to make sure you know what the solution is. In this case, the solution is I decide to schedule the event or I decide not to schedule an event. You keep it or don't keep it. Now, some solutions are valid and some aren't. In this case, a solution is valid if no events that you scheduled overlap in time, right? You don't want the NRA people with their guns to overlap with the vegans. You know, that just won't work. Right? So, then what is the cost of a solution? In this case, it'll simply be the number of events scheduled. You assume everybody's paying you a fixed amount of money. All right? Later, we'll look at the problem in which people give you different amounts of money for the events and stuff, but then we'll have to wait for dynamic programming. All right? For greedy algorithm, all events are the same, and you just want to schedule as many as you can possibly schedule. All right? So everybody understand what the problem is? Right? We have these events which are tells you the start time, finishing time. Schedule as many as you can. All right. So here's an example. Time is kind of going in the obvious way, and a purple line tells you where in time it starts and where in time it finishes. And you want to schedule them so they don't overlap, and you eyeball it, and what's the obvious answer? You take the top, right? That's the obvious answer. All right, so we need a greedy criteria. First, we have to come up with the algorithm, all right? And the algorithm is going to be a non-adaptive greedy algorithm, which means you look at each event. So here's one event. You look at it, and you decide some criteria about it. You give it some number. And then we sort the events based on that criteria, and you go through the events in that order, and then as you go through the order, you have to commit to either taking it or not taking it. And what's the obvious way? So one thing you also have to decide is how to decide whether to commit or not. But if you're grabbing the orders in the events in the order that you like the best, then you take it unless it overlaps with what you've committed to already, right? So which event here do you think we should commit to first? Which one looks kind of you like the best? Shortest ones, right? So that's good. Shortest criteria first. It looks like it's really good. So how many people think that this greedy algorithm works? Anybody think it doesn't work? Anybody doesn't know? All right, good. Here, motivation is, well, the advantage of getting a short event is that it doesn't take up your room for very long, and you still get paid for it, right? So it certainly is a good motivator. And I bet you that, in fact, I'm quite sure that you're going to get it within a third or a half of optimal if you do this, but you won't get optimal. Right, so here's an example. Everybody see this example? Proof by example that it doesn't work. Right? Can you see that? If you go for the greedy, you're going to grab that middle short guy, and you're going to be dead. Right? Because the optimal took the other two. And then kind of proof, you can sort of see, well, maybe this argues that you're within a factor of 2 of optimal. All right, so let's look at so here's another example. What's the optimal here? Is, you take every other one. All right, so anyway, we need another greedy criteria. Any other greedy criteria you can think of? Who invited him? Tell him to leave. Anybody else? Did you come up with that on your own? Yeah. All right. He can be my grad student. All right, so here, greedy criteria, earliest starting time, right? You want to do every other one, maybe earliest starting time. Does that sound reasonable? It's not, right? You want to, I mean, one motivation for this is it's kind of fair. The first guy comes, gets the event. Anybody give me an event, a set of events where this doesn't work very well? It's a really long one, Just because he comes early doesn't mean he leaves early, right? So that's bad. All right. So we need another greedy criteria, and we're going to go for the. Here's one: conflicts with the fewest other events. Right? Now, first off, is this a greedy criteria? It's not really, right? Because you're talking about how the events overlap with each other, right? It's not really just looking at one event. But, it's still, you can figure it out. Anyway, here's a counterexample, right? You see, these overlap with lots, right? So you're going to schedule this one, but that was wrong because you should have scheduled those. All right, so again, we're looking for the criteria, what's true about, those are the guys you want to schedule first, and he already told us the answer, if you listen, right? We're going to go for the earliest finishing time. All right, what was your motivation for earliest finishing time?
Get them out as quickly as possible.
Exactly, get them out, right? We don't care when they come, we want to get them out. Very good, all right. All right. We schedule the event that will get them out as quick as possible, right? All right, so here's an example, all right? We want to schedule these things. So that's the guy who finishes first. We say yes to him. Then he finishes next, but why do we say no? It's because he conflicts, right? Then the next guy, we say yes, we say no, we say no. You just kind of go through this, right? Everybody kind of follow what we're doing? We're doing them in order of finishing time. We say yes if they don't conflict with a green one, right? Everybody kind of get the algorithm? All right, so what we need to do for these is you have to first say, be sure what the question is. What are the objects? What choices? What's the solution? What's the cost of a solution? When's the solution valid? And then you need to come up with the algorithm. All right, so the algorithm is you're given all these events, you sort them based on finishing time, you start by committing to nothing, you go through the events in order of finishing time. If the event doesn't conflict with somebody you've committed to, then commit to it. Otherwise you reject it and you keep going until you're done. Everybody, the algorithm's good? All right, so now, in our proof so far, we've described the algorithm. The question was already there, so you don't have to describe the question. You have to describe the algorithm. And the way you describe the algorithm is you tell me the greedy criteria, what order you're going to look at the objects, and then you're going to tell me, well, when you get the next object, how do you decide, make the decision about it? Usually it's you do the best thing degree thing unless there's a good reason not to. And that's the algorithm, right? And then you need to have a proof that it works, all right? And to have a proof that it works, the first thing you need is you need a loop invariant. And this you should all memorize because I want to see it verbatim on the test, right? You don't need to have them gone wrong. You can either put that or not. But this you need. There is at least one optimal solution consistent with the choices made so far, right? So what does that mean? That means your little brother running the algorithm is at the top of the loop. He's committed to some objects already, right? Some events he's committed to taking, some events he's committed to rejecting, and the rest he hasn't looked at yet, right? And we know that we don't know an optimal solution. We have no idea what optimal solutions are, but we know there exists one consistent with what the algorithm has done, right? And if we want, we can assume the fairy godmother is holding it. Right? Everybody good with this paragraph? So you have to say that. Then you have to establish the loop invariant, right? So you can write this down. It's always good to write this down because I'll put a check next to it when you do. And how do we establish the loop invariant? Right? At the beginning, the algorithm has done nothing. So is the loop invariant true? Right? Well, assuming that there exists a solution, there exists an optimal one. And assuming that optimal one is consistent with what the algorithm has done, because the algorithm hasn't done anything yet. All right, so there's another paragraph which you can memorize and put it down just like that. And then we get up to this. You can write this down because I like putting checks next to them. Right? Then we say, well, the loop invariant, what does it give us? We're at the top of the loop, the algorithm has done some things. And we know there exists an optimal solution consistent with those choices. Let's give it a name. So you give it a name, and you might as well use my names because I like my names, and then we'll all be writing the same thing down. All right? And I'm going to be, when I'm marking your things, being really looking to make sure you understand what this is. All right, what is this? It's an optimal solution, meaning a decision's has been made about every event. And it's a valid solution, right? No events overlap. And it's optimal, right? And I don't know what it is. The algorithm doesn't know what it is. But it is consistent with what the algorithm has done so far, and the fairy godmother is holding it. Everybody got that? All right. So then we go around the algorithm again. The algorithm looks at the next object, the next event, and either commits to it, right? Commits to it if it doesn't overlap with what's been done before, or if it overlaps, rejects it. And now our goal, then we need another paragraph, and the paragraph is going to say, all right, the fairy godmother is holding this. I'm going to give some instructions to tell her how to change this into this. All right? So you need a little paragraph which describes how she does it, how you're going to do it. And there has to be steps in which you know that she can always do it. You're not going to tell her to do something really weird that she might not be able to do. All right? And then she now has this, right? We assume this exists, and from this we constructed this thing. And now we have this thing, right? And this has to be one paragraph by itself, because if you in general, if you merge all these paragraphs, then often they can become wrong and muddled, right? If you have separate paragraphs, then, right, you don't want to prove things about an object until you've defined it really carefully, right? So you define this object. Now we have this object, and we need to prove that this object is a valid solution. Well, how do you prove it is a valid solution? Well, this was a valid solution, and I made sure I didn't mess that validity up, right? So you can have a paragraph which says, this was valid, I didn't mess that validity up, so this is valid, right? You'll have another paragraph which says, oh, and when you say this, when you're writing this paragraph, I'm going to be looking to make sure you know what valid means, right? In this case, valid means know when the events overlap in time, right? So in this one, consistent with previous and new choices. What does that mean? That means, well, this had the property that of the events that the algorithm committed to or rejects so far, this thing does the same, right? And what's this one here, we have to prove that it's still consistent with those previous choices. We didn't mess that up. But we also made sure that it was consistent with what the algorithm just did. What the algorithm just did here. Right? Everybody following that? So in this paragraph, you have to be clear what it means to be consistent. You mean consistent with what the algorithm. And so then you say this was consistent, and this is consistent as it was before, plus it's consistent with this new step. So you have a little paragraph saying that. And now, finally, you need a paragraph proving this is optimal. So you need to know what optimal means. In this case, it has as many events as possible, right? This had as many events as possible. We massaged it so that the number of events either stays the same or miraculously goes up. Right? Does that make sense? Paragraph, paragraph, paragraph. Then you'll have one little sentence at the bottom which said, because we proved that this thing exists, we know that it exists, and hence the loop invariant is true. We've maintained the loop invariant. Everybody get that? Then, all right, so now this is just redoing those steps, all right, more precisely. All right, so she's saying, I have this optimal solution, witnessing what's going on so far, right? And he commits to the next event, and he's going to say how to change what she's holding, right? Change this into this. All right? And we're going to do proof by picture, because usually that's good enough. Right? So in this picture, the algorithm has committed to these 4 events and rejected these events, hasn't considered these events. Right? The optimal solution has these events. You'll note, I don't know, you can believe me that that's optimal, and they don't overlap in time. Everybody going to see that? So the fairy godmother is holding this. Now, the algorithm, it's sorted them by finishing time, so it's considering this event next. Right? And it's going to decide to take it. So the algorithm takes that one. Now, I need to tell the fairy godmother how to change her solution into another solution, right? So anybody want to tell me how to do that?
You drop the long one and then you add the short one?
Right, right. So first step is we need that in there, right? So the first step is put it in. And then the second step is to tell her to drop things. Now how do we know to tell her what to drop? Well, let's just be bold and say, put that, oh there it is. You put that one in and drop any event that you're holding that conflicts with what we just put in. Right? Everybody good? That was our instructions. Now, first, we have to prove that what she's holding now is valid. Right? How do we prove that it is valid? Well, anybody want to know how it's valid? Yeah. Well, we put somebody in, right? What we have to say, what we had before was valid. It didn't have any overlaps, right? We stuck one new event in. That may have created new conflicts. But we just said, take out any conflicts, right? So usually when you're doing these various steps, some of them are easy and one of them is hard, and you don't know, it depends on the problem which one's going to be hard. It depends on how you word it, right? We in fact worded it in such a way that this is easy, right? We constructed it to be valid. All right, consistent. How do we prove that this is consistent? What does consistent mean even?
It doesn't affect the stuff that you've already done in the past.
Right. All right. Right, exactly. So consistent means it still contains these, it still doesn't contain these, and it contains this. Right? That's what consistent means, because that's what the algorithm has done. Well, we made sure it contains this. Right? We didn't put any of these in. Right? So the only danger is that these guys dropped out. Right? Could they have dropped out?
No.
they only drop out if this overlaps with those, right? How do we know that this doesn't overlap with those? The algorithm took it, right? Why did the algorithm take it? The algorithm took it because it didn't overlap with those, right? The algorithm took it because it didn't conflict with what it's done in the past. Everybody good with that? So there's a little sentence that says, yes, it's consistent, right? And, all right. Now, optimal, how do we prove that it's, yeah?
Sorry, can you just go back to the last point? The algorithm took it because it didn't conflict with those ones, but it did conflict with the left one. Why did it?
All right, because this is what the algorithm has done so far, right? The algorithm has never considered this, right? The fairy godmother had it, but this is what the algorithm is committed to, and then the algorithm looked at this, right? So what we threw out may be some of the things that the fairy godmother has, but we don't throw out anything that the algorithm is already committed to, right? Does that make sense? Optimal. Well, yeah. We put one event in. What do we want to make sure? We only take one out, right? We don't want to take two out. If we take two out, then we're in trouble, right? So all we have to prove is that when we put one in, two don't come out. All right?
I thought you said that you have to throw out all the events that conflict them.
Yes.
You said that you multiple.
Well, that's what we have to prove doesn't happen. Exactly. Right. So exactly what he said, I put in one, it's possible that two come out, right? And we have to prove that that doesn't happen. Now, I'll tell you right now, this proof that we're going to do right now, I think is a little harder than I would expect you to do during a little test. Everything we've done so far is exactly the kind of thing we're doing, right? And this little bit is a little harder, and, you know, if you just muddled around and said, you know, if you'd gotten to as far as, you know, I put this one in and two, I have to prove that two don't drop out, and oh, I hope two don't drop out, you know, because life is good. Then, you know, you get, you know, if everything else was perfect, I would give you, you know, chances are I would even give you 100 for that, right? But it depends on if everybody said that, then I might lower the marks. All right, so this is what we want to prove, that you only delete at most one. All right? So we're trying to prove you don't delete at most one event. Let's look at these events that we might delete, right? Consider any two J's that might get deleted, right? And we look at properties of them, right? The one property is that the event that we care about, the event I, it finishes before these guys finish, right? Because they're events that the algorithm hasn't considered yet. So that's one thing we know at J, is that they finish later. Right? So this is what I was saying here, is that the finishing time of the guy we care about is less than the finishing time of the J. Another thing we know is that I conflicts with these guys. Right? Why are we deleting, why are we throwing these out? It's because I overlaps with them. Right? So we know I overlaps with them, and we know they finish later, so they must be running at this time right here. Right? Does that make sense? And if they run at this time right here, what do we know about them? They overlap with each other. And if they overlap with each other, what do we know about the fairy godmother? She only has one of them. Does that make sense?
Like you had J and J prime.
Yeah.
But they didn't overlap with each other. They just I was overlapping. Was the overlapping factor? Like
right. Well, if this is, they have to be after.
Right.
Right. So they can't then both overlap with I.
No. Like what if the second one? See, I is in between the two.
Oh, but then we would have considered this one before we considered I. Right. That's the whole point of the sorting them by finishing time. So that's just the things I was saying. Right? So that means only one of them was in the optimum. And so what we did is we assumed that this exists by the loop invariant. We gave an algorithm for massaging to this. We proved that this was valid, consistent, and optimum, and hence we've maintained the loop invariant. Right? Everybody good with that? That's only case one. Case two is the algorithm rejects an event. All right? And so what do we say then to the fairy godmother? He says, well, our algorithm rejected the event, so you better have rejected it as well, right? Why did the algorithm reject it? It's because it conflicted with what the algorithm is committed to already. But the fairy godmother has to be consistent with what the algorithm has done, so it would conflict with what the fairy godmother has done already as well. Does that make sense? So in this case, we know that the algorithm, the fairy godmother has also rejected it, and so we're good. And then we have to have one last paragraph in the end, which says loop invariant exit condition and code gives us the post condition, right? And what do we say here? Everybody should have this memorized already. Loop invariant says by the exit condition we've committed or rejected each event. Right? That's why the algorithm stopped. And hence the algorithm has a solution. Right? It's made a decision about every object, so the algorithm has a solution. And the loop invariant says that there exists an optimal solution consistent with these choices. Well, it's made a decision about each, and if it's consistent with all of these, this must be what it has. So this says what the algorithm has is optimal. And when the code returns that, and we're done. The post condition is we returned an optimal solution. Everybody good with that?
Good.
All right, and again, they're very fast, right? Now, the one thing in this example that takes a little bit more time is that you have to keep checking whether this new event overlaps with previous guys, right? And anybody have an idea how we can do that quick? Do we have to compare this with all previous ones?
No, the last one.
No, we just have to compare it to the last one, right? We keep track of the last finishing time that we've accepted, and we're good, right? We just compare it to the last one. All right, you ready for another one? All right, so this is a classic. Nobody should, I think there's a law, it's probably written in the Constitution, nobody's allowed to graduate from computer science unless they do minimal spanning tree. So what is the minimal spanning tree? Is that the input is an undirected weighted graph. And the output, a solution is a subset of these edges. And there's two requirements of it. Well, it's a valid solution if it contains no cycles. All right? So a tree is actually a connected no cycle thing. Right? In this case, it's not even connected. But, right? So we want a subset that's a tree, and we want it to span the graph. And what the span mean is for any two nodes, if you could get there in the original graph from one to the other, you can get there in the blue edges. Right? You can get anywhere that you could get before. Right? Does that make sense? 5 minutes. All right, we're probably not going to finish this in 5 minutes. All right, so what's an application is, imagine these are cities, and they need to run power lines to connect all the cities together, right? And they calculate for every pair of nodes, they can calculate how much does it cost to run power line from here to here, right? And if they get a minimal spanning tree, then it will get to all of the cities, and they want to do it in the cheapest way possible. All right. So the cost of a solution, of course, is the sum of the edges that we've taken, and our goal is to find a minimal spanning tree. Everybody understand the problem? And so our algorithm is going to be greedy. We're going to look at the edge that we like best. All right. So here, first off, we need a greedy criteria. So which edge do you think looks best? The smallest one. All right. So you go for that one, and we take it. Why do we take it? Why not? Right? There's another one. We take it. There's another one. We take all these ones. Right? We keep taking ones. The 2, we take it. 2, we take it. A 2, we take it. A 2. Do we take that guy?
No.
No. Why?
Circle.
Creates a cycle. Creates a conflict. Take him unless there's a good reason not to. Right? So then we keep going. Do we take that one? No. No. It creates a cycle. Right? You take that one. You take that. Oh, we can't take that one either. And I think we're done, in fact. Right? Everybody get the algorithm? So, oh, I guess we're going. So we're just checking the rest, and we're done. All right, we have to prove that this is acyclic, but by definition it's acyclic, right? Because we didn't add things that created cycles. And you also have to sort of prove that it spans everything. We could prove that, but let's not worry about it. It does. Now what we're going to prove now is prove that it's optimal. Oops, I did that little thing. Come on back. All right, so this is called Kruskal's algorithm. There are two famous ones, Kruskal's algorithm and Prim's algorithm. And the way my mind works is I know one of them's Kruskal's and one of them's Prim's. And if you tell me which one's the right, then I know the other one's the left. But this one happens to be Kruskal's. You sort the guys based on their weights. You go through them, and you grab the next one as long as it doesn't create a cycle. Right? So that's the entire algorithm. And so we're going to go through our steps just as like we did before. First one, to prove that, first you have to tell me the algorithm. What's the algorithm? You need a greedy criteria. What's the greedy criteria? We sorted the edges based on their weight. Then we have a criteria which says which, you take that next edge, do you keep it or not? Well, you keep it as long as it doesn't create a cycle. Right? That's the algorithm. Then you need a proof. You need a loop invariant. The loop invariant says we haven't gone wrong. There exists an optimal solution consistent with what we've done so far. Everybody, really, seriously memorize this. Alright? And then we have to establish the loop invariant. How do we establish it? Well, at the beginning we haven't made any choices, so any optimal solution will be consistent with this. Alright, so here's a little one. You have to prove that there exists a tree that spans the graph, but there doesn't. Are we out of time now?
1 minute.
1 minute. I got 1 more minute, but you can come in. All right, so these same steps that we're going to go over, right? So in our minute, we'll do this again next class, but let's kind of get a sense how the algorithm is committed to some edges and rejected some edges. And she's claiming that she has a full optimal spanning tree, right? She claims she has that, and then the algorithm commits to some new edge, right? And we have to instruct her how to massage what she has into something else, and then prove that that's valid and optimal and consistent. And I don't think we have enough time to say how to do this. So next class, we will finish this, and I will try to look at your tests. But I really don't want to. I'd be happy to simply burn them.